right, so our first presenter today is Yuyao Wang, who is a master's student with Professor Heron.
Thank you. Hi, everyone. So today I'll be presenting on my research, which is the position estimation of an auto-rotor permanent magnet synchronous machine using linear Hall effect sensors and a neural network. Okay, yeah. So this is what I'll be going through today. So to start off with, I'll be a brief recap of the permanent magnet model and control of it, as well as an overview of existing methods of doing the position estimation. Afterwards, I'll be moving on to the experimental setup, as well as some preliminary results and further work that can be done in this area. So to begin with, the most popular control method for permanent magnet synchronous motors is the field-oriented control. And the main reason for this is it simplifies the control of this PMSM greatly. So it utilizes the Clark and Park transform to change three-phase variables into DC-like components. And on this diagram over here, you can see that after the Clark and Park transform, what you get is a D-axis and a Q-axis, with the D-axis aligned to the rotor flux. And what this achieves is that you get a simplified expression for the torque, which in the case of a permanent magnet machine only depends on ISQ. So therefore, the control of the PM machine is simplified such that is somewhat similar to a DC machine, and your Q-axis current directly controls the torque, whereas your D-axis current in this case affects the flux in the machine. So you can just apply control on one variable and have it run pretty efficiently. However, to achieve this field-oriented control, it requires a knowledge of the rotor angle to align the reference frame, which is this theta here. And as I mentioned just now, torque only depends on the Q-axis current. So a precise measurement of this rotor angle is critical in achieving good maximum efficiency and maximum performance in this permanent magnet machine. When there is an error in this measurement of this angle, what you get is that your reference frame is not perfectly aligned to the actual reference frame in the machine, and so you are using some of your currents will go to the D-axis, which is wasted in the case of a permanent magnet machine. Right. So some of the current methods that are used to measure this rotor angle, they can be roughly divided into censored and censorless methods. So in censored methods, there's resolvers and encoders, and both of these requires the physical attachment of a sensing device, a position transducer, onto the rotor and stator, which increases cost, complexity, and as well as failure chances. Alternatively, there's also other methods of using sensors, which is Hall effect sensors with a model-based algorithm. Some of these will be like phase lock loops or zero crossing detections. And on the other hand, sensorless methods are more popular because they reduce the complexity of the whole system. And these are in general two approaches. The first of which will be the back electromotive force-based methods. So how this works is that the main idea is to look at the three-phase voltage waveforms coming out of the machine and use it to derive the rotor angle. But the key weakness in this method is that at low speeds or zero speed, what you get is that there is no back EMF term in this case. So you will not have a significant signal, and at low speeds, the signal will also be dominated by the resistive term, will be affected by the resistive term. So the accuracy suffers at low and zero speed. The second method will be rotor saliency-based methods. And so how it works is it tries to inject a high frequency signal into the machine. And the key feature that's required for this is that both the D-axis inductance and the Q-axis inductance must be different. So there must be a salient feature in the rotor. However, in the case of some PM machines, like the NASA machine, where there's no salient features at all, this method will not work at all. And there are also other downsides, such as increased hardware costs and complexity, as well as hardware overhead for injecting the signal and additional losses. So both of these methods has its own weaknesses. So what is proposed is we use an array of Hall effect sensors to measure the leakage flux, leakage field from outer rotor PMSM. So we are using outer rotor PMSM in this case because it provides easy access to the rotor field, but it's not limited to outer rotor PMSM specifically. And the signals from the Hall sensor array is passed into a neural network, which is trained to estimate the rotor angle based on the readings from these Hall sensor arrays. And the benefit of using a neural network in this case is that it does not need to have any knowledge of the modeling of this PMSM or any of the specifications such as the inductance of this. And furthermore, when the operating conditions change, or for example, when the PMSM is switched for a different one, where the first one is failed, it can be easily retrained to accommodate the changes. And this is how our experimental setup was run. So on the left picture, you can see that over here, this is the plastic arc holding 10 blocks. Each of these blocks has one small linear Hall effect sensor attached to it. And this is a block diagram of the whole system, where there's a outer rotor PMSM, and the Hall sensor array is hovering around a few millimeters above the surface. And this is also mechanically coupled to a resolver. Both the resolver and the Hall sensor arrays are sampled at the same time regularly with a microcontroller, and the data is passed into MATLAB for training of the neural network. And this is a sample of the waveform that we can see from these Hall effect sensors. So a key point is that you can notice that there's this large region of a plateau, as well as these inflection points near the middle. And this creates problems for this system because these features make it no longer a one-to-one mapping from an electrical angle to a sensor reading. But this is in some sense mitigated by having multiple sensors, such that when one sensor is in the plateau region, we have another sensor that's in this more or less linear region that we can rely on to infer the angle from. And so by having these multiple sensors, a shallow neural network is used with these multiple sensors as input, and a shallow neural network is able to, in a sense, memorize these sensor readings at each electrical angle and form a correlation between a set of sensor readings and a targeted electrical angle. And so furthermore, with a permanent magnet machine, because of its finite torque ability, we don't expect the direction or speed to change drastically. So furthermore, a recurrent neural network could also possibly be used, wherein it also takes in as input the previous prediction of itself. And so this is a possible method to improve the estimation accuracy based on the past state of the system. So we took several data sets, and each data set consists of sensor readings with a certain speed and a certain direction. And roughly we have around 7 data sets with a slow speed around 100 RPM or a slightly faster speed at around 300 RPM, and also in both directions, clockwise and counterclockwise. And using this for training, 70% of each data set is used for training. A random 70% and a random 15% for validation of the training, and the final 15% for testing of the neural network performance. So these are the preliminary results for the neural networks. So in this case, on the graph, you can see that in the blue is a shallow neural net, and the green is recurrent neural network. A key point to note is that the shallow neural net performs pretty consistently across all of our data sets. despite it only being trained on the slow counterclockwise data set. Whereas you can see that for the recurrent neural network, it shows a very strong bias for a certain direction. Since it was trained on a counterclockwise data set, you can see that for all of the counterclockwise data set, it shows a much better performance compared to the clockwise data sets. So this suggests that the recurrent neural network can be, in some cases, better performing than the better or equal performing than a shallow neural net, but it has to be trained to accommodate for more cases. And this graph, this histogram shows the distribution of the errors for a shallow neural net, and this applies to most of the other errors for the recurrent neural net as well. So what the best result we achieved was that there was a mean of 1.1 electrical degrees, with 60% of the errors less than the mean, and 90% of them are less than 2.5 degrees and 5% greater than 3 degrees. There are some single error points greater than 6-7 degrees, but those are in the single digits and can currently be attributed to noise in the system, which we are looking at eliminating. Right, so this shows that a neural network can be applied to do position estimation in a permanent magnet motor, and further work will involve verifying the performance of this neural net at different conditions such as higher speeds as well as higher torque loads. And also a possible method to improve the performance would be to optimize the sensor placement. Right now they are all in a single radial distance. By varying the distance and varying the location, there's potential to improve the performance as well. And lastly, it's more of a stretch goal would be to integrate with a sensorless back EMF method, wherein you run it open loop and use the back EMF method to predict the angle and use that as a training target instead of a current resolver. And then use the neural net to augment the back EMF method at the lower and zero speed region where the back EMF method suffers from poor accuracy. Right, so that is all I have. Questions?
Good. After you.
When you say optimize sensor placement, is that just directly talking about distance from the sensor, or like distance between, like the placement between the sensors, or what?
Right, so right now we have them all in one arc and all at the same height. So we saw that in some sense, varying the height gives you, alters the measured waveform a bit. You get it more sinusoidal, but you also reduce the amplitudes. So you get less of a resolution in that sense. So we think that by having some of them closer to the machine and some of them further away, as well as maybe having a different set somewhere else, we'll have better improvement.
So a couple slides earlier, you talked about the error, like you had like 1.1. Like what's your target for error? Like what's acceptable, and how much of an impact does it have to kind of, like you said, maybe you have more DQ currents than you intend?
Well, right now we don't really have a set target. We are just trying to minimize it as much as possible, but it's in the end limited by our whole setup. So the resolver has its own precision, and the resolver to digital converter board has its own precision. So both of these will limit how low we can go. And in terms of performance-wise, I think that is still dependent on the application of it. So how much of the torque, of the starting torque, for example, can you afford to lose, which will determine how accurate you need your angle to be.
How would this error compare to like a resolver?
I'll say the resolver is probably 0.5 or lower.
What would happen if you were to have a non-metallic rotor? When
non-metallic casing on the magnet? Because we're talking about the NASA motor, automotive machine. What if you were to just have like carbon fiber or something like that?
I don't think that matters because right now we are not touching the rotor at all.
So you don't think the metal doesn't disturb the magnetic field?
Well, it affects it. It changes the shape of it definitely. And based on simulations, the NASA motor has a pretty sinusoidal field external to the carbon fiber as well. So that is, in a sense, that is better because it's more sinusoidal than this machine, right? So because ultimately the neural net is trying to memorize it instead of looking at what waveform is supposed to be. So the metallic casing alters it, but it doesn't affect it to a large degree.
For the data that you showed initially, the first experimental data that you had that said normalized readings.
Yep.
Yeah. So what is that? Like, what kind of field are you
B field.
getting over there? Oh, that's B field.
B field converted to voltage. So it's linear Hall effect sensors, and zero field has a bias voltage, 1.5 volts, let's say, and positive goes one way, negative goes the other way. So to use this data for training, we subtract out the mean first. So bring it down to zero, and that's what normalizing means. And that the numeric value is just the voltage values. And it doesn't really matter whether it's B or voltage because it's just numbers for training. All right, that's it. Thank you.
Here, you could
Just say, all right. All right, so our next speaker is Adriano Abrantes. It's 10 minutes before. But Adriano graduated, got his master's degree in Brazil, and is here doing his PhD with Sir George Gross.
Thanks. Hi, everyone. So today I'm going to talk about flexibility metrics and flexibility in power systems. So this is my outline. I'll talk about why flexibility matters. What are we trying to achieve about flexibility? Give a quick review of a couple of flexibility metrics that have been proposed and got some attention. Talk about RAM products which were implemented in MISO in California and how they relate to flexibility, how they can help to provide flexibility and the future directions of our work. So the climate change impacts are what are driving the introduction of renewable energy in power systems. And in fact, many states have renewable power targets. These are the renewable portfolio standards, which require load-serving entities and some utilities to have a certain amount of renewable energy to supply their load. So they have these targets by a certain year. They have to meet this amount of renewables or this percentage of renewables. And this has been fostering the development of renewable energy in the country. Some states like Texas, they actually went far beyond their target. And I think there are other states too. And so there's a big problem with this because wind power is not aligned with the load. In fact, many times is going down when the load is going up. We have more wind power at night than during the day. And this imposes higher ramps for the controllable resources to meet. So for example, in this moment, we can see that the load is ramping up when there's absolutely no wind at all. And here the load's going the load's going down and the wind's going up. And so for the controllable resources, this is a steep ramp down, and some generators have minimum output limits, and so they might just stay on and pay to generate, and this causes negative prices. And so these are some of the problems that come from the penetration of renewable energy resources in the grid. So we talk a lot about the net load, which is the load minus the wind. And so in this figure, you can see that it's much more variable than the load itself that the ISOs were used to dealing with. The ramps tend to be steeper. And this is the duck curve that came from California, where they made predictions that solar penetration would cause this dip in their net load curve, and they think it looks like a duck. But so it becomes a big issue because, especially for this ramp here, because you might decommit a lot of units in this stage, and as the load starts picking up and the sun's going down, you might not be able to ramp up fast enough to meet that load. And so this image shows the solar output separate from the load and the wind. The scale is different for the load and the renewable output, but you can see the impact, right? So you have an initial morning pickup load, which in some of the states, some of the ISOs, it's the main challenge. And many times the wind's going down when that load is picking up. And then now, because of solar, you have this additional ramp down, which was not a problem before. And then later, the sun starts going down and people are going back home from work, and there's load increase with renewable output decrease. And so one of the impacts of not being able to follow this net load is to simply curtail the renewables away. And you can see in 2009, ERCOT did a lot of that. And the way they managed to solve this, to lower this, was by investing in transmission, making sure that there would be fast-acting resources that could compensate for the variability of the wind. Another impact is the prices of energy. Like I said, when the solar is in and some generators are going to be needed in a few hours, they're going to be kept committed even though they are generating its minimum and they're not economical at the moment, just because they're needed later. And so prices become negative, and in fact, prices become very volatile in general. So when a system does not have enough flexibility to meet its requirements, you see a lot of negative and volatile energy prices. You might curtail some of your renewables. You can have high real-time unit commitment costs. So you had a forecast that there would be some renewable output in, say, like 4 hours, and that was wrong. So you might have to commit units for these 4 hours, and you can no longer use all the resources you have in the system. You can only use the resources that can be up in 4 hours. So you're going to pay the price for that. And also the high uplift payments. So when you're keeping resources on, even though they're not generating at all, you're going to pay them. So they had a startup cost. They had, they're not selling all the energy that they could. And so this caused a lot of side payments in the grid. And so to provide flexibility, we have the typical fossil fuel generation. Some states have some storage resources, like some hydro plants. Curtailable loads, right? Demand response is increasing, but it's not that much yet. But these are the controls that the ISO has. And so the committed controllable resources have to make sure they can provide the ramping capability to meet these net load variations. And to improve flexibility, you can improve the way you operate your system. For example, we have a day-ahead market and a real-time market. The real-time market is usually something like 4 hours before the actual time. So perhaps having some market in between that is not 24 hours ahead or not just 4 hours ahead can help mitigate the impact of this uncertainty of these load forecast errors. Also, increased demand response provides another degree of control over the net load. And as the problem in Texas, deliverability of flexibility. You might have the fast-acting resources in the system, but because of congestion, because some of the lines are at their limits, you cannot actually deliver those ramps. And investments in resources such as energy storage and fast start resources such as combined cycle gas turbines that can ramp up, ramp down pretty fast, and that can start up and be shut down for a short time. So our objective is to develop a framework that we can assess flexibility, say how flexible a particular grid with a particular set of resources and flexibility requirements is. And we want to be able to tell this system A and system B which one is more flexible. And each system will have its particular properties. And so if we can do that, then we can say, oh, system A, if we add this resource, how does this change the flexibility? And we also want to be able to say, what's the economical value of flexibility? How much it costs to provide it? So these are the goals that we would like to achieve with a flexibility metric. So one of the flexibility metrics was proposed by Lanois in 2012, and it's pretty much based on a reliability index, which is the loss of load expectation. So this is done in planning studies. You consider that each generation has an outage rate, right? They tend to have an outage every like 1 hour in I don't know how many days. And so you build a probability distribution of the generators to be out, and you look at, you have a load duration curve. You see when your load is this high and the periods that your load is actually not that high, and you find how frequent loss of load events are, how frequently the generation will not be able to meet the demand. So this is when you take the expectation of the occurrence of these events, this is the loss of load expectation. And so they proposed something analogous, but to flexibility. So they said, how frequently is the system not going to be able to meet its ramps? And so that was the IRRE, the insufficient ramping resource expectation. And it does provide useful information, especially for planning, but it doesn't tell you anything about the cost impacts of it. Like, so you can meet a ramp. How much did that cost? Like, did you have to commit a unit that was shut down and you're going to have to pay for its startup costs just to make sure that if there is a higher load than expected, you're going to be able to meet it? And so in 2016, Zhao and Litvinov, they proposed a framework based on robust optimization. So they have a forecast for the load a few hours ahead, and they say, well, given a cost limit, what is the load range that I can meet? And so this is delimited by the black lines, and then the gray area is based on historical data. What are their net load forecast errors? And they'll say if they expect a problem or not based on if the gray area is contained in the dispatch range that they can provide at that cost. And so operators really like the robustness approach. They don't like to have a probability of meeting a target. They like to make sure that they'll meet it, even if it's not that economically efficient. And this tool provides a nice visual effect for the operator to consider when there's a problem, when there's a concern. But the economics of it is just saying, oh, you can be this far at this cost. And you could try to use this to compare different systems or the same system with an additional resource, but you're always going to be saying like based on this cost cap. And so one way to improve this would be to actually have a function showing the relationship between the cost cap and how these black lines get away from the expected dispatch. And one of the other means that were taken to provide flexibility is the ramp products. This paper by Wang and Hodge show an extensive review of these, what they call flexible ramping products. But basically, it's guaranteeing that at each period, T0, T1, T2, T3, you can guarantee a certain ramping up capability. So you say that if the load is somewhere in that area, we can meet it. One problem of this approach is that then thinking that you can be here and also here might not be realistic, because from here, you cannot ramp this much. You have to ramp at the same rate as you're ramping here. But the flexible ramp products or just ramp products are already implemented. So a generator doesn't simply offer their energy, but they offer their capacity and their ramping capability. So if the ISO has a requirement for ramping, they might pay the generator just to keep it ready for them. And so this impacts the cost of production, right? And also impacts the uplift payments. Some people say, oh, it will reduce the uplift payments because the generators are getting an additional revenue. But the thing is, the revenue from RAM products is not as big as the revenue from energy. So this is not clear yet how the RAM products will impact the side payments or the uplift payments. But they do provide information on flexibility. For example, the prices of ramps indicate how valuable the ramps are for operation right now. And say you have a flat load to meet, then you are going to pay nothing for having ramps available, right? However, if you have like steep ramps, the price for the ramps is going to be high. And the ratio between the prices of ramps and the price of energy actually says something that you can use to compare different systems that can be very different in nature, very different in size, but they have a certain price for energy and a certain price for ramps. And if you look at how these prices, what's the ratio between these prices, you might be able to say how flexible a system is or isn't. This also allows you to do an analysis that is location-based. So we have prices for energy based on location, on which node of the system they are. And we can have the same kind of prices for the ramps. So a ramp will have a different price at a different node, and this can indicate that we have a flexibility problem that is highly related to congestion in the grid, not just lack of ramp capability in the controllable resources. And so what we're trying to achieve is to develop this framework, which is based on robust optimization. So we do want to make sure that there is a region where the dispatch may lie within, and say, well, based on the prices of the ramps and the prices of the energy itself, can we compute metrics that relate to the impacts of flexibility? So this metric has to increase, and then we have to see also the increase in the flexibility impacts. So the increase in the curtailment, the increase in the volatility of the LMPs, and so on. And then if we're just going to be looking at prices in different times, in different time horizons, and in different places, this can all be incorporated in this flexibility metric. And that's it. Any questions?
Do the changes in price, you mentioned negative prices that arise from this much energy, does that affect both the suppliers and the users, right?
Yes.
How much industrial response is there to electricity prices? Like, I don't know how you can respond, like, I don't know how you can quantify it, but is it significant, insignificant?
So in the 598, I think Professor Bose talked about this once. It's not that big yet, but there are companies that once the electricity prices are negative, they're gonna draw electricity and get paid for it. Yeah. Yeah.
I noticed the map at the beginning had Hawaii as 100% renewable by 2045, I think. Does that include nuclear, or does each state consider, or do they get to decide whether nuclear is renewable or not?
I'm not aware of anyone considering nuclear renewable.
But nuclear industry tries.
Yeah, I've seen they claiming it's clean. And
Oh, so though, do different states consider, is it just renewable or is clean in two separate things? Or do some states just say, no, it's clean energy that they're shooting for?
yeah, this is state dependent for sure. And I think what usually keeps nuclear power plants online is mostly jobs, because if you shut down one of these plants, you can impact a whole town and so on. But from my knowledge, typically the nuclear is being kept away from the renewable label, but they still manage to stay on just by talking to the politicians, saying, "Oh, you really want to lose all these jobs under your term?"
Why, are they gonna do a lot of like tidal?
I think offshore wind is the biggest one. Offshore wind, mostly a lot of wind.
On the sea.
Yeah.
Yeah. Yeah. Yeah, but if they want to achieve 100%, then they'll probably need a lot of storage too, and yeah. Yeah. Oh, all right. Well, thanks.